Well, welcome everybody. It's really wonderful that you're here at the Heart Research Institute in this rainy afternoon. And the news I have for you tonight is the science fiction writers of 30, 40, 50 years ago are all turning in their graves. And they're turning in their graves because they never imagined that the sort of things that they predicted as being ridiculous are now have been done. And we're really on to the next phase of life in this area. And we're just so lucky at the moment to be alive at a stage when the whole world is actually renewing the way they think about the future. It is what has been totally impossible, maybe even a decade ago, is now possible. So this is what we're going to be talking about tonight a little bit. And this is what keeps us totally awake at night in trying to figure out how to relate to all the new technologies that happen. But before I expand on that a little bit, I'd like to acknowledge that we're a land of the Gadigal people and pay our respects to their ancestors and the people here, and past and present, and the whole Institute is very much concerned in making sure that Indigenous health improves as much as possible, as quickly as possible, and all the technologies we have available are also applied to them as quickly as possible as well. But I don't think either our Indigenous forebears or us imagined what is now possible to do at the moment. And I'll just simply mention a couple of things. First of all, cellular engineering has had an enormous advance over the last decade. The fact that we were able to take outside our bodies any type of cell and grow any particular organ or mini organ is just totally astounding. And this has really revolutionized the way you do personalized medicine. And you'll be hear a little bit about that in the next few minutes. The second huge area has really been that of robotics. What took me 3 years as a PhD student to do, we can probably do in about a day and a half now. It condensed discovery into milliseconds, what we're taking hours. And this robotics has also resulted in the generation of an enormous amount of data. And AI is really in a situation, our friend, in trying to handle all this data. I can't explain to you easily how much data there is, but imagine standing in the rain out there and for about a square kilometer trying to capture the only one raindrop that's falling down that has the information that you need. It's impossible. It would be impossible. But AI is capable of identifying that raindrop that contains the information that you need to actually make your next discovery. So AI is not only useful for getting robots to work better, to analyze data, but also to design our future experiments and design clinical trials, which is a really important part of actually fine-tuning the way our discovery works. So we're very, very lucky to have 3 wonderful speakers here tonight that will talk about various aspects of cellular engineering, Carmine, Elle about her experience with the medical profession, and Geoff about AI and magnificent databases. And also, so thank them for coming, and thank you for coming. And I'd like to just point out to Peter McGoran, the chairman of our board, is also a part of this audience. And I think we're very lucky as an institute, not to have many of our scientists here, but also the board who is really interested in what we do. And I'm very lucky to have so many supporters as you, who also want to be informed, and we're very delighted to tell you as much as possible about what we do. So thank you very much for coming, and I'll hand over to the wonderful Katrina.
Thank you. Thank you for that really engaging and very informative introduction to this evening. Good evening, everyone. Thank you so much for joining us tonight for our latest Heart to Heart seminar series. Tonight, it's set to be a really interesting conversation. We're exploring the topic of technology and AI in cardiovascular research and its impact on patients. By way of introduction, my name is Katrina Dowling and I lead the Development, Philanthropy and Communications team within HRI. And I'm pleased to see that we've got some familiar faces here tonight and lots of new faces too, both here and online. When we launched Heart to Heart, our intention was to open up our doors and to give people the opportunity to come in on a regular basis and really stay up to date with our work and have the opportunity to connect with the research team. So it's really pleasing to see that we're building with each seminar series and that we're gathering momentum. So thanks for being here with us tonight. For those of you who are unfamiliar with HRI, we're an internationally recognised medical research institute, and we're focused very much on investigating the causes and complications of cardiovascular disease so that we can develop better diagnostics, treatments, and cures. We were established over 35 years ago now, in 1989, to fuel both basic discovery research and translational research. And today we are comprised of 15 different research groups and centres, each focusing on a very specific element of cardiovascular health. And we have more than 100 really dedicated team members working across 2 sites here at our Newtown location and also at the Charles Perkins Centre across at the University of Sydney. And the team is really focused on delivering cutting-edge research. And as an organisation, we've got a real commitment to nurturing the best and brightest minds, the rising stars and the next generation coming through in researching cardiovascular research. And why does all that matter? Well, put simply, we want more people who are impacted by cardiovascular disease to have more time with the people that we love and care for. That is what drives us every day. So let's get underway tonight. We're all very familiar now with how AI technology and has permeated our everyday lives, whether it's FaceTime ID on our phones, smart devices in our homes, or the simple art of drafting an email with the assistance of ChatGPT. These emerging technologies and AI have, of course, impacted the world of medical research and clinical practice in dizzying ways, and that's going to continue into the future. This evening, we're exploring how artificial intelligence and emerging technologies are transforming the way that we understand, diagnose, and treat cardiovascular disease, and what that means not only in the lab, but in impacting people's lives, real patients. So we're very fortunate tonight to have an outstanding panel with us. Associate Professor Carmine Gentile is a globally recognised expert in the field of 3D bioprinting and stem cell technologies. Carmine heads up the Cardiovascular Regeneration Lab here at HRI and is an Associate Professor within the School of Biomedical Engineering at the University of Technology, Sydney. Carmine's recent work has focused on novel molecular and cellular approaches to treat cardiovascular disease based on the use of 3D printed mini hearts, which are just fascinating. And he's developed those for the use in human heart tissues. Professor Geoff Strange is a health research leader with a special interest in big data, artificial intelligence and their application to further our understanding of structural heart disease. Geoff is a senior academic lead at HRI and has over 20 years of clinical and medical affairs leadership experience in both hospitals and the pharmaceutical and medical device industries internationally. He's a professor within the Faculty of Medicine and Health at the University of Sydney and the School of Medicine, University of Notre Dame. And finally, and very importantly, we have Elle Pendrick with us tonight, which I'm very excited about. We always love connecting with Elle and spending time with her. Elle brings vital patient perspective. She lives with complex congenital heart disease and has undergone 5 open heart surgeries, which I just find mind-blowing. And you've got the possibility of more surgery on the horizon. Yeah. So Elle has an very inspiring story to tell. She's launched a book called Adulting Well and is a passionate advocate for cardiovascular health and improving the patient experience. So thank you to the three of you, not the three of us, the three of you for joining us tonight. All right, so I might start with some questions, looking at the big picture and emerging technologies in AI. So Carmine, there's a lot of excitement about emerging technology in cardiovascular research, including in your own field of cardiac regeneration. From your perspective, what are the most important technological advances right now, and how are they changing what's possible?
Thank you so much, Katrina, for the introduction, and thank you everyone for being here. Where to start?
It's a big question.
Big question. Being told I have 5 minutes to address that. So in summary, I could tell you that we are in a very lucky time, given the fact that, based on my personal experience, working in a research area where we aim to build body parts. When I started in 2006, when I moved to the US in the first time, I didn't have access to the stem cell technology that we have nowadays. Making stem cells from patients' blood was not possible back then, and that really helped us to move ahead with our technologies nowadays. Obviously, AI is there as a technology, as a tool, as well as bioprinting. I would like to put that in context. When I first started working in 3D bioprinting or biofabrication, or whatever you want to call it, basically building organs and tissues using cells and biomaterials. In 2006, I didn't have the opportunity to even explain my peers what I was doing, because to them it was out of this world. Nowadays, I can talk about this to anyone, and they don't find it anything important anymore.
It's very important.
The technology out there is actually available. It's more importantly for me what you do with it and how you employ in the different aspects of your research journey. For instance, there are different examples.
Long time. It's a sequential process. And we're just trying to figure out how we put all that together. The other approach is big data, big, massive, retrospective, real world information about everybody in the room. So now I can put all of that together and I can find out where different things cluster. I know that, the 3 redheads in the back corner have X, Y, and Z, and the people with blue eyes in the front. I can figure out exactly what the trends are now in amongst the total cohort. And so I don't have to see every single person every single time in every single clinic visit to put you all into a clinical trial prospectively to figure out what's going on. I can understand the clusters of relationships amongst all of the individuals. And so that's what we're doing. We're taking really big data, proper ginormous data. We're talking about billions of records, something like 2 billion text strings about every single person's heart and exactly the terminology that was used in the report. We're talking about 93 million hospitalization records and every single DRG code and every single ICD code, which is the International Coding of Disease, on exactly what you had and what your hospital admission was like and how that related to your cardiovascular disease. All of that stuff coming together is going to really transform the way that we're operating as a healthcare profession so that we can impact the individual with the joint knowledge of the group technology.
Well, great. Thank you. Thank you, Geoff.
Did I answer your question?
You did.
Cool.
Thank you. Elle, you've experienced the healthcare system now over many years, and you've had multiple procedures, as I said earlier. Can you tell us a little bit about your journey, your story, and something about your treatment journey as a patient with complex congenital heart disease?
Yeah, sure. I'll echo the welcome to everyone. It's really nice to see you all. So I was born in 1983 with complex congenital heart disease in a little place called Wagga Wagga, not too far down the road, to two parents who had never heard of babies having heart disease. And within 3 days, they'd whisked me off in an air ambulance up to Sydney. I'd had my first open heart surgery at 3 days old. I really had no concept of what that was like until I held my nephew at 7 days old, and we sort of sat there going, wow, okay, I'm getting it now. And throughout the rest of the journey until now, when I'm 43, it's been quite a journey. I've had about 20 surgeries all up, most of them catheters, which I'm like, oh, it's only a catheter. And people are like, no, the heart surgery, you need to include that. And 5 open heart surgeries at the ages of 3 days old, 6, 8, 21, and 33. So I'm on a good stint at the moment at 43. So we'll see how we go. But it didn't occur to me until my 4th open heart surgery at 21 that my heart disease was essentially incurable. The surgeries are a temporary fix, and essentially what they do will either disintegrate or might stop working. It's just a matter of time. You don't really know when that's going to happen. The technology over the years has definitely improved and has shaped the rest of my life. So living with heart conditioning, it basically impacts everything from how much I can work, where I can work, my exercise, my relationships with people. Not really, I mean, I'm 43, I'm not going to go out raging anyway, so I think that's a big, but also mental health and finances. A lot of the treatments can be quite expensive, a lot of time off work and sort of trying to manage all of that. And as a woman with a heart condition, it's also a lot of everything from periods through to menopause that you have to consider as well. So technologies have intervened in different parts of my life and they have been incredibly helpful.
Yeah, great. And you're entering what you've termed uncharted waters, aren't you, in terms of your survivorship relative to other people before you who've had congenital heart disease and what that presents for you in terms of menopause and road ahead.
Absolutely. And I think with congenital heart disease that we are now at a really great stage where people are surviving into adulthood. The question is, what does that look like for us now that we're hitting our 40s, 50s, 60s? And that's been tell us.
So we might go to Carmine first. So Carmine, you touched on your work in terms of lab-grown cardiac tissues and mini hearts, and it's really incredibly innovative. Can you tell us a bit more about your work? So how are emerging technologies like 3D bioprinting really shifting the goals? And what are some of the challenges that presents and that you're working through?
Thank you, Katrina. So that's a really important question. And also thanks to my dual appointment between UTS and HR, I actually was able to explore this part and embed it more into a clinical space. And my meeting, Elle has actually provided me with ideas on how to implement the technology. We started off by looking at the medical problem and basically how heart failure patients actually nowadays are dealing with the disease and why the heart transplant is still the gold standard and what the limitations are. So wrapping up 20 years of research that is summarized on the flyers on your chairs. In summary, we've been able to develop this technology where we can take, as I mentioned before, blood from a patient and then make the stem cells for a patient that then develop into a personalized therapy. That personalization helps to avoid any immunotherapy, which is typical of a heart transplant. And in this way, we are able to develop this miniature version of the heart that somebody might say, why do you want to create a miniature? Well, we actually learn from nature that step by step, that's how organs and tissues are built. And so by looking at how this happens in a human body, we learn how to implement these steps in our test tube to build these mini hearts. And then the next step was for us, how do we personalize not only the therapy from a cellular point of view, but also from a treatment type of point of view. That was also a follow-up with in interaction with artists. So we have artists that do residency in my team. It's a little bit of fun outside the regular work. But the first artist that we created was basically based on a 3D printed human-sized heart. That was the first time for us because scaling up in stem cell technologies is quite expensive. But it was helping us to understand how we design all the mini hearts basically embedded in the bioprinted patch that would not fit the requirement to be typical of the patient. In summary, the patch will not adhere, will not be morphologically, anatomically adapted for the patient. So nowadays we have an area of my team that is personalizing the patch from the cellular aspect, and another one together with obviously with the clinic to understand how to personalize it from a morphological and anatomical point of view. And where is AI fitting in all of this? Well, we don't want to waste our time. We do know that patients are they're requiring potentially a new treatment. And so just to give you an example, the first bioprinter we brought from Spain, we don't use it anymore because it's been over 10 years now and technology has advanced so much, but we recently tested a new bioprinter, again from Spain, from a different company, but an AI was embedded in the printer itself. Why? Because if you can imagine printing a piece of paper like this one, you would have some information, some parameters. When you start printing cells with materials, the complexity goes up, out of the roof. So a student can spend months, if not years, in optimizing these steps. The camera attached to the printer was able to analyze all the different prints and improve the printing as it was going. So that really pushed forward the research that we are doing in our lab. And that's just one of the examples.
Yeah, amazing. So it's really enhancing your ability to deliver personalized solutions.
Correct.
Yeah.
So, and then obviously there are other aspects that we are exploring, how to potentially test this in a faster way to enter clinical trials. It's really important because, especially with the recent FDA modernization Act 2.0 and 3.0, alternatives to animal testing, including in silico, aka computer-based simulation, or Matthew touched upon organoids or other type of technologies, can actually help us to move into clinical trials. And so that's been recognized as an opportunity internationally. Also, how to move closer to the clinic by using a combination of these technologies.
Okay, great, thank you. And Geoff, you are focused on developing and managing really significant patient registries, and I understand you're managing the world's largest echocardiograph registry with over 110,000 individual records. Yeah.
1.3 million
1.3
Australians.
million. Okay, yeah, that's amazing. So I completely
Close
underestimated
to
it.
110.
Yeah, close to
We're getting
110.
there.
We've got a little bit of a gap. Well, yeah, that just emphasised my point that it's huge.
Yeah.
So what insights have emerged from the ability to process these very large data sets, and how might AI help us to answer epidemiological questions that were previously very hard for us to answer.
All right, well, this shouldn't take too long. All right, so the first part of the question really is dealing with, what does the big data tell us, and how can we understand things that we may not have understood previously, right? Have I got that right?
Yeah.
Cool. So if you think about structural heart disease, so there's 4 basic valves in the heart, and there's 4 basic chambers, and the blood flows from the top on the kind of left to the bottom, out to the body, back around through to the top of the right, and it kind of does this figure eight, right? Layman's term, kind of infinity curve, right? That's flow. So in amongst all of that is each of those valves are opening and closing, the heart's contracting and relaxing, and we're trying to figure out exactly what's going on with small data sets, which means I've only got, a small selected group of people here that I'm trying to understand what's going on. I take the mean or the median, the average, or the middle section, and I start cutting the data one side to the other, and I look at different outcomes, and I go, everybody on this side does pretty well or pretty badly, and everybody on this side does well or badly, and that's my cut point. What we're doing with big data is we're going, okay, what's the true statistical distribution of the entire population? Okay, what is the real mean? What is the real average of a large group of data set? And where along that trajectory of the disease progression does mortality start to change? So we're doing that with simple kind of statistics that are fairly basic. But then when you take a disease like aortic stenosis, for example, which is a stiffening of the aortic valve sits at the top of the ventricle, and it basically opens and closes to get blood out to the rest of the body. If it fails, you're in quite a bit of trouble. So what we found is that historically, we've been looking at how the valve opens and closes. How stenotic is it? How stiff is it? And what is the gradient between above and below that valve? And what is the area of the valve? So, okay, that's an old approach. With artificial intelligence, what we've been doing is saying, okay, if I take every bit of input vector from every aspect of the imaging technology of that heart, line it up as an input vector, send it into a deep neural network. So we're talking like 2,500 different nodes across 4 or 5 different hidden layers, and all of that multi-dimensional relationship between what matters and what doesn't matter in the independent or the dependent nature of all of those different contracting, moving, valve opening and closing, blood flowing, vortexes, etc. parts, what matters and what doesn't matter. And actually what we did is we said, okay, across all of those hidden layers, this is our ground truth. Learn from everything that you know about the echo or the heart and predict this outcome. And what we found was that the things that we were relying on, the indices that we thought were important, in fact, weren't important. It was the way that the ventricle responded, the way that the heart muscle responded to that stiff valve that predicted the outcome. And this has revolutionized the way that we're diagnosing these patients. And so this particular invention went through the regulatory process with the US FDA, and it's now being utilized in the United States to help diagnose patients with aortic valve disease. One really good example, and we're taking that and we're applying it to the congenital heart disease population. And we, in fact, just today, we finalized a paper where we've used a number of co-clustering works. This is with one of our colleagues, Will Baxter from the HRI, and works with David Salameyer and myself here at the Heart Research Institute. And basically what we've identified is that there's hidden clustering groups within groups that we hadn't seen before. And so the artificial intelligence is allowing us to see the self-organized relationships that are within the groups that we thought were separate groups. And so it's separating the inseparable to allow us to now phenotype these patients and hopefully do a better job.
And I think that's a really important point, because I think, broadly, there's often a lot of fear associated with the concept of AI, but it's a classic example of how it's actually, enhancing your work. In no way, replacing people who are involved in doing the work or the project, but enabling you to do a much better job at investigating the data that you have before you.
Absolutely. And I think that, part of that is the regulatory environment that we work within, and how we work together hand in hand with regulators to allow them to bring technology in that supports clinical decision making, that doesn't replace it.
Yeah.
We don't want to replace us as humans. That would be crazy. We want to actually be human. And that means that we get to then interpret a machine learning algorithm and apply it clinically to that one patient that's right in front of us. And that makes a huge difference because, you know, it's just given the fact that we are human, at the end of the day, someone reading a report or reporting on a scan of some type, it's a different report than it is first thing in the morning. It just has to be. It's just like pre-coffee, post-coffee. We're humans, right? It's the way life goes. So if we can democratize that and we can make sure that we can have the same result for every patient at every scan point, in every interaction with the healthcare system, and we can take the learnings that we've had with big data, apply it to the congenital heart disease population, apply it to all structural heart disease, we're going to really make huge strides forward in the way that we treat them. Now, epidemiologically, these are two really, really important groups, right? So the structural heart disease group, we're so underserved. So in Australia, last year, there was 9,000 aortic valves replaced in this country. My data suggests that there's 100,000 patients living with aortic valve disease right now that meet all the criteria to have that valve replaced. That's 10% penetration, if you like, of who we're finding. Now, when we first looked at the population of congenital heart disease, you know, we thought that we might find 20 to 30,000 individuals. We've got 120,000 individuals right now. And we're learning so much about this emerging population that are surviving into adulthood and how we can change the way that we approach those continuums of care, the models of care, to ensure that there's the aspects that we're learning from interaction with our colleagues to figure out a better way of serving that population as well.
That's terrific. And you touched on the issue of regulatory frameworks. Do you think we have the right expertise and regulatory frameworks in place at this stage? What needs to shift?
Yeah, that's a great question. So I think there's probably three things. Always put things in groups of three. It's easier for me to remember. So one is that we've got to figure out, and AI, I want to go back a second because AI is not just AI, right? There's different forms of artificial intelligence. If you think about a large language model, which is what a lot of people are familiar with ChatGPT, that basically searches the information on the web, comes up with an understanding of what the amount of information is and answers your question on, you know, where the best restaurant is up on King Street. So that's one large language model. But if the information that it says is that the Thai restaurant's really good, but only 3 people gave that information, and it turns out it's a bit shit, oops, it's not very good, then the information that comes back to us is not going to be great. So we need to work with regulators to make sure that the information that we're using is curated well.
Yeah.
And that's our job as researchers, is to make sure that we don't just take any data from anywhere, that we work together with our cardiology colleagues, our engineering colleagues, in a co-collaborative way so that we can get really good curated data that's either well labeled or well put together so that we can rely on the interpretive ability of the artificial intelligence to execute. So the regulators need to help us do that because they need to put stipulations around the data sources that we use. And us as researchers need to make sure that we're collaborative and we don't just bunker down in our own little world and do what we want to do, that we open up our vision so that we can get the right information to apply the right technology to it.
That's great. Thank you, Geoff. Thanks. Now, Elle, looking back over your years as a patient with CHD, you mentioned before that technology has advanced through the course of your treatment. Talk to us a little bit about how that technology has evolved and how it's been applied in your care. What are the shifts that you've seen?
Well, I think the biggest shift is I'm sitting here. I survived. It really is the biggest shift. There's not much else. I think there's so many decision points along the way that have improved, and you know, from a technological perspective, I've had 5 open heart surgeries, and I can tell you what, the pain management got a whole lot better. I mean, and that's research and technology that helped improve that. And rehabilitation is a new thing, and exercise for people. And as much as that's not big technology. I wear a smartwatch for a reason. It helps track my heart rate when I train. It helps me train within a particular heart rate and helps me make sure that I can stay within that. It really has revolutionized how I can exercise, along with the HRI research in exercise for people with CHD project. That was massive for me. It was an absolute game changer. And that really helped. And I think as a patient, sometimes research such as the things that these guys are doing, I don't always see it, but I benefit from it and hear because of it. And a lot of people don't necessarily see that, but you know, we know things like My Health Record, which has come online, and other digital health records are so helpful. And we think, in my mind, I'm like, okay, that's great. For example, if I went to the GP and they're a bit slow on giving me my blood test results, I can just go look it up myself now. That's different. And that's so much better for me to manage things quickly. But on the flip side, Geoff here is data mining it.
I'm not data mining it.
All right.
You're ethically.
Ethically mining my data. And he's getting all the information to be able to then get better outcomes for people with CHD, which I don't necessarily see. But because I've, subscribed to some of those new technological advances, there's a whole bunch of other things that can happen and support that. It's definitely helped with medical devices. So I've got a heart valve and a bovine stent, and they've lasted quite a long time. And I know that, quite a long time ago, they didn't necessarily exist. And I think now for some people, the research is there, but it's sometimes the access to it. As, Geoff was saying, you've got nearly 90,000 people who maybe haven't access the surgery that they need, and that's something that you find out from big data and things that if the technology is there, then it's how do we access it and make sure people get to it as well. And I think HRI are doing a really fantastic job of being able to do those kinds of projects that really make a difference. And for me, I know that my bovine stent and my pig's valve obviously came from animal material, and I would very much like if you could personalize it, please. Nice. We have a lot of jokes in my family about being hot pig.
That point, Carmine, everything you've talked about in terms of 3D bioprinting and the action of the mini hearts and the patches. How far away is it from clinical practice as you see it? What are some of the challenges and obstacles in terms of getting there?
Thank you for the support, Elle. Yeah, we are trying our best from the bench side into progressing this. We are aware of the regulatory limitations, especially when your medical device becomes a biological. Then the regulatory pathway becomes more complicated. And then if you include the fact that it's personalized, it becomes a nightmare. And that's internationally, there are different current regulations. It's getting better, also because some of the regulatory bodies are engaging with the scientists to provide feedback. It's an ongoing process, but understanding on how to progress into a clinical trial that is not cheap, will cost millions of dollars, and also obviously has an impact on the patients and where to run the clinical trial. For instance, I always give this example to my students in class. Imagine I run a clinical trial in Italy. What is the relevance of that in Australia? The population is different. Similarly, the regulatory body looks into this type of demographics. So it's really important to understand how to study strategically your clinical trial to basically bring it to the patient. Where do I see it going? Obviously, AI is improving how we are progressing. It's becoming more embedded on what in our daily practice. I would say that probably in 10 years' time, we won't even call it AI anymore. It's going to be like part of our daily life. Similarly to what we're seeing happening with bioprinting, it's going to become the centrifuge in the lab in a few years' time. We're going to lose some of the excitement beyond it. which is a positive aspect, but that really opens up new venues of how we progress this. Ideally, we would love to have, as a scientist, and I've worked in this space for 20 years now, have the bioprinter in the hospital, having the clinician trained, whether it's for heart application or others. There are bioprinters that are already present in hospitals in Australia and overseas for different applications of cardiac. And then potentially have that as a tool to basically help in the clinic on a daily basis. But we are a little bit beyond that yet. But having said how everything has progressed from the beginning, with my experience, I think there is still hope for that.
Okay, terrific. So we're at preclinical trial phase at the moment, and the
yeah.
next stage is clinical trials.
All right.
Yeah. Okay. Terrific. All right. And Geoff, Elle touched on the concept of data mining.
I'm actually a guest here tonight. You of my own free will. Yes, please.
So they talk to us about in the management of big data sets.
Yep.
What are some of the big ethical issues that you need to work through, and how are you effectively working through them?
Yeah. So it's actually a very serious and really important point. Consent is a process that is difficult in big data sets, right? So when you go through and you work within the guidelines of the National Health and Medical Research Council, there's a stipulated guideline around consent, around the consent process, around informed consent, a thing that's called opt-out consent or a consent waiver. And all of those things have stipulations and guidelines to them to ensure that you adhere to good clinical principles and ensure that we do the right thing by both ourselves as researchers, but as well as patients and the general community. So consent is difficult. When you go to a lab, or if I go and search a database in a hospital, so let's say we're working with our team down at Royal Children's Hospital, for example. Now I'm going to take all of the patients from Royal Children's Hospital and work on an approach to extract all of that information to feed it into our big data set. So can I go around now and go back and ask every single patient, do they have consent to use their secondary sourced information that has no impact on their clinical management, but it just takes it from this repository and puts it in this repository, but this repository happens to be joined to this one, this one, this one, this one, this one. So how do I deal with that consent issue? Can I ask the ethics committee for a waiver of consent? If you go through the actual NHMRC guidelines, absolutely I can. And that should be a really normal thing, because the harm to the individual is no chance that could outweigh the benefit to the community. It's just not possible. So consent's a big issue. How we deal with that with big data is going to be a problem. We I said earlier on, we've got a database full of 1.3 million Australians. You can't consent in a clinical study that's funded by the normal processes, every single person. So you ask for a consent waiver of their retrospective information that's already been collected. Now, when we're moving forward, if you're using that to start building commercial products, then that's not going to be acceptable. So how do we translate the learning into a commercialized outcome that's good for the community? Because it's no good us just having our data and we know what we're doing with it. We have to translate it into something that's meaningful. And if we can't do that with that current consent process, then that's a real nightmare. So those ethical dilemmas are a big issue. I don't think that storing data these days and making sure that the cybersecurity is in place, they're not really big problems. I mean, we all log on to our banking details, don't we? We haven't lost. I mean, there's a little bit of money get lost every now and then. Probably not a great example, actually. But I don't think that that's the biggest problem that we've got to deal with. I think getting the consent right and making sure that people are happy with the use of their data is really where the rubber's going to hit the road as we move into really big data sets.
And presumably a lot of data isn't, it's anonymized in any sense.
Yeah, well, there's two types of processes that you have to do. If you're going to link someone's data to their mortality record, then you need that to be identified. But once it goes into that mortality record, the federal government have what's called the National health data hub now, which is, and it's in what they call a seed pod, which is a secure environment for the analysis of data and in your own private pod, so that they basically quarantine that information, and everybody that accesses it has to go through these extraordinary processes of security to be able to access and do the analysis inside those secure environments. So I think we've got that one covered, mostly.
So now, Elle, you've talked about how technology has sort of helped you be here and has advanced along the way. If you were to put on your sci-fi hat and think about, patients that will come after you and who are coming after you, what would you like to envisage as being some of the way that technology will advance and how AI may be applied through patient care? What's the dream?
Well, the dream is to go from survival to thriving. It's not just, we've moved past purely survival. It's now about, the whole person and the whole and living well. I think that's really important. And I think the future looks like less invasive procedures, more personalized products that you can get for yourself, and that essentially will improve everybody's outcome. And from Geoff's research, putting on my sci-fi hat, really it's about connection. And for me, growing up, I didn't know anybody with congenital heart disease. It wasn't until I was in my mid-30s that I started to meet other people through volunteer work and things like that. And to hear Geoff say, "Oh, just so you know, there's 120,000 of you out there," it's like, that's amazing. And we're working now on, okay, so you've got an amazing database of information about Australians with congenital heart disease. What do we want to know as a patient out of that? And that's something that we're working with them on, as thinking into the future and using the AI onto the big data set is, what's the distribution around Australia? Where do we mostly live? What's our trajectory? What's the how, those sorts of basic questions that we want to know about ourselves, because congenital heart disease, a lot of it was unknown. This is, we're the first generation to survive. And so now having a data set like this and using AI to be able to tell the stories of all of us around Australia is absolutely incredible. And it connects us in a way that's really hard to describe.
Yeah, that's terrific. So I think those two key points around connection and less invasive procedures would be absolutely life-changing.
Yeah, I would prefer not to have a sixth open heart surgery.
Absolutely. And I can understand that.
That's very fair.
Yeah. And I wanted to congratulate you too on the brilliant work that you've recently finished up doing with the World's Heart Organization in terms of the new paper that's been released. Tell everyone a little bit about it.
Thank you. And so I worked with World Heart Federation over the last 6 months, and we just launched their annual report, which focuses on congenital heart disease. And you won't believe it, but one of the recommendations is data. It's getting good data. It's incredible. And I can't tell you how proud I am to be on the core working group and here, obviously globally in developing countries, data is an issue. And she'd be like, so Australia has the largest one and it's run with HRI. I know the people, that's amazing. It's an incredibly proud moment to be able to do that. And the report's out now, and it's the first time the World Heart Federation has focused on congenital heart disease. It's often an invisible disease, and I'm sure a few of you that I met this evening were like, "Oh, Elle's here. We don't know anything about her," and now you know a little bit more. You don't necessarily have to look sick to have heart condition, and that's sort of one of the biases that we're trying to work through as well.
It's a brilliant piece of work. So yeah, well done to you. Now, I'd like to thank the three of you. It's been a really fascinating conversation, and I think we've only just started scratching the surface. So I'd like to thank you all for your time. And I'd like to give everyone now the opportunity to ask questions. Are there any questions that people have? And no question is silly. Yes, up the back, Gary.
Gary, I'm a consumer person with cancer, and I've recently got involved with a cancer, lots of cancer consumer contributor to a research grant. to do with brachytherapy. So that's treatment of prostate cancer using seeds. And this particular research paper is about big data. And the problem with brachytherapy is that treatment occurs within centres, and the statistical information data collected in the analysis is kept within the centre and it's used to inform treatments within the centre. Now it's been recognised currently across the research community and therapy of cancer treatment that is rather limiting along the lines you were saying of it being a background level, and if you can identify where particular people sit outside that, it informs the process. Anyway, here's a particular background I'm working with is in quality assurance of brachytherapy treatment programs. And what the key part of it is defining the inputs to this big data so that all the inputs are consistent within it. I'm wondering in your area, is there an existing consistency in the inputs across the world or whatever the size of your sample is, or is that something you have to tackle as well in defining what should be the inputs or how you define the inputs?
Yeah, that's a really good question. I think so. There's two levels of collecting data. One is on a registry level where you want absolutely consistency so that you're getting the same information on every single patient, but you're defining what that is. So you're sitting around with your colleagues, your consumers, your group and saying, okay, what do we need to construct that gives us uniform registry information that every patient is going to bring in? It's selected because it's selected based on your own knowledge, right? So it's a known question. You can't ask an unknown question because you don't know what you're going to ask because it's unknown. Or there's the other approach, which is what we took in our first approach, which was to take everybody that's having a particular test. It's unselected. There's no selection bias in the way that we take that data. We take everybody, whether you get a normal scan, whether you've got an abnormal scan, whether you've got disease A, B, through to Z, doesn't matter. We take everybody. And so that way, we don't get always complete data on every single person, but we get a real world example of exactly what's happening to everybody and we don't miss anyone out. So those two models are a little bit different in the way that you start off your research. For the congenital heart disease program, we sat down as a steering committee. We had everybody from the pediatric cardiothoracic surgeons, the adult surgeons, we had the cardiologists, the respiratory physicians. We had everybody together. We had the nurses, the nurse practitioners, physios, the psychs. We had everybody sit in a room and go, okay, how can we construct the right questions to extract from the data that's out there? So there's two different approaches. My kind of philosophical view of big data is that you should take everything. And if you can do that, that's the best way to do it. That costs lots of money. Data storage is complicated. The ethics is complicated. The collaborative agreement you need between colleagues is complicated. And with congenital heart disease, it's even more complicated. When they have decided globally that we need these big databases, it's going to be an interesting journey because the nomenclature or the coding is coded in multiple different systems. And we've had to overcome that with match-up tables from different coding. So there's the European Pediatric Congenital Coding System, there's the International Coding of Disease, and it's been in version 7, 8, 9, and 10, and now 11. And so all of these different versions of disease coding need to be matched up in a way so that we're talking apples and apples. So your point's extremely important. Thank you for raising it. Hopefully I answered that with either side of the coin's okay.
Microphone. Good question. Heart research. Who sits above the Heart Research Institute in terms of your data acquisition?
Can I just clarify? I've got the question on who sits above the Heart Research Institute as far as data acquisition?
Correct.
So the data is acquired under routine clinical care. So that's just general service delivery from a health service perspective for patient X or Y with disease A or B. That then goes through a governance structure through that institution. So let me give you an example. So let's say we're taking data from the Prince Charles Hospital in Brisbane. We have our local ethics committee here at Royal Prince Alfred Hospital. That ethics committee would give us approval to approach the governance group at Royal Prince Alfred at St. Prince Charles Hospital.
Right.
Prince Charles would then go to their governance and ethics committee, who would then review it and say, yes, you're right, or no, you're crazy. And then that goes to the Public Health Authority in Queensland, who then give approval for the Prince Charles guys who approved it to give them approval to give it to us. And then on top of that, there's a data transfer agreement, and that data transfer agreement gets signed by the Prince Charles Group, the PHA, the Public Health Authority,
Privileges and stuff.
to give up to us. And then we, as the humble researchers, as the data custodians of that, in the beginning, we take responsibility. But what we've done is collaborated with the HRI. And so we've got an overarching organisation that takes responsibility of that data
So you're
custodianship.
independent of HRI?
The data sits independently, but it's the custodianship is through the
So we
HRI.
host it.
Yes,
Yeah.
that's a nice way to put it, yeah.
Yeah.
So individuals always own their data. That's just the way life goes in the health system.
You're a consultant external to HR?
No. I'm employed by the HRI. I've got a research grant through the New South Wales Health, and it funds the work that we do with
So
HRI.
all those requests go through HRI up to Prince?
No, they go through the hospital network. And then there's an agreement for it to come into a central repository. So the hospitals are the guardians and the public health authorities
Where's
are
the
the guardians
collaboration?
between the hospitals and the institutions and patients.
Chris?
I've got two, if that's all right. Just on the back of that conversation about data, Elle, as somebody who has their data used, at what point would you be tempted to put your hand up and say, no, I don't want my data used for this? You're now crossing the line.
I think if it was, if there was publications with my name on it and my health data, then that would cross a line for me, but that's not what this is at all.
No, I know. I'm just
Now,
asking.
personally, for me, if I gave consent and said, yes, please use my data, that's fine. But if it was used unknowingly and it was clinical data, my personal story is out there, and I'm glad that people know that and they can learn from it. But I think clinical data is slightly different, and I think if someone got into my records and then shared those.
So if you found that your data had been used, your medical data had been used for somebody to elicit a profit, would that be okay by you?
Well, that's a good question. I haven't thought of that. It depends what the profit is, I guess.
So like if it went into a wearable technology that somebody like Garmin or Apple could then use to predict AF or some other heart condition, would you be happy that your data was used to help inform their prediction because ultimately you're providing a greater good to the community? Or would you be a little bit annoyed by that, the fact that your data is being used to help somebody make a profit and you hadn't been consulted directly about that?
For that particular example, I would personally be okay because they're not taking, on my wearable, they're not taking my name and my address and my phone number and putting it into something that's then published outside. They're taking, okay, so when Elle trains, she goes to 130 beats and, and that's what she tries to keep to. And then we've noticed that when she pushes too far, it goes into AFib, atrial fibrillation. So, and then that goes into something else that they can make a better device from. And it's anonymous. Yes, I'd be happy with that. But on the flip side of that, my thought is, I don't know, I have congenital heart disease.
Yeah.
So how good is the data that they're getting? Because they don't know anything about me apart from I wear this.
I just thought we talked about
Yeah.
Geoff and how he was using the data. It was
Yeah.
good to get your
I love
perspective as well.
Jeff using Attenders.
My second question goes to Geoff. Thank you for your answer. My second question is, Geoff, your data can make some incredibly powerful predictions. How do you validate them? Is it a case of going to an animal model? Is it a case of waiting and watching over time to see if the hypothesis that you're making is fulfilled in the cohort that you're looking at? Or, do you use another means to validate, or do you use everything?
Yeah, it's an important question. And I think there is a number of different ways of doing it. I mean, what we're trying to do is invert the relationship to research, right? Instead of having a very narrow window of inclusion, exclusion, small population, extrapolate that to the rest of the population, that's fine. We're going the other way around and assuming that our hypothesis actually is correct around that particular disease state that we're looking at. But external validation is critical here. So the artificial intelligence that we built for the aortic stenosis modeling that's now approved by the FDA, that was validated at Harvard. So we did an anonymized replica of the model, completely independent, detached, deployed in their center. They took their data, they took 60,000 patients, ran the model over it and validated that way. So external validation on a de novo population is incredibly important. And I wouldn't be trusting any artificial intelligence that hadn't been externally validated outside of the research group.
They were great questions. Thanks, Chris. Are there any other questions that? Yeah, Tom.
Great panel as always.
Oh, thanks, Tom.
Just a question for Carmine, just in regards to the mini heart project, so it's preclinical trials at the moment. What's the timeline here? I mean, given if we have the funding available for this critical. It's on for the question actually catching up with Elle where we're at. So we have analyzed the preclinical trials into understanding how to bring the cells together. Today I was talking to my postdoc onto basically which way we go down the path, whether we cells or not. Hopefully I can share this data with you guys soon. The next question for us is how do we actually implement this into clinical trials? And mentioning before about the FDA Modernization Act 2.0 and 3.0 into how to move this forward, whether animal testing is required. And when we're talking about animal testing, small animal, large animals. And going back to Chris's question, do you do everything? Do you do stuff? We are evaluating at the moment how to implement our results to basically take them to the clinic as soon as possible. Our hope is still that we can move forward in the next 5 to 10 years to the clinical trials. Funding will be a huge will have a huge impact, of course, depending also down which path we go to. Running a clinical trial overseas will have a different cost than running here in Australia.
So to get us to clinical trial phase, in terms of funding, what's needed at present?
Well, there are a few things. We're talking about the consumables. We're talking about funding the scientists. We have students. We have postdoctoral researchers. Equipment. The equipment that we have changes over time. As I mentioned earlier, the bioprinter we brought to CERN in 2016, we don't use it anymore. At UTS, we have 9 different types of bioprinters through the support of the university and then fundraising. We do not only use the bioprinters, we also do R&D on them. We've done a lot of material characterization, testing something that is valid in an animal formal model that does not really translate into a patient, especially if you're trying to replace treatment that would last for 10 years. And so this is where we are focusing on right now. Basically all the support for consumables and equipment and the personnel. The running a clinical trial right now would be around between the $2 and $5 million. We took a step ahead. We created our in-box clinical trial. So we created a replica of patients' hearts that we call as a bioreactor. And so we study how the patch develops and changes and performs under conditions that are similar to what happens in the human body, not 100%, but close enough. And that's been developed at UTS in collaboration with HRI, and we are the only ones in the world that have it. Thank you. Thank you.
Now, we're running over time at the moment, but it's really great to see so many interesting questions pop up. So I think we've got time for one final question. Has anyone got a yes?
Thank you for the lovely talk. I have a question, Professor Geoff. Do you think that there'll be an avenue for people to like voluntarily give a data? Because health is like holistic, there's like diet, exercise, genetics. So do you think that there'll be an avenue for people to eventually like give the data voluntarily, like as only thing like that for sake of research?
I mean, the short answer is yes. The long answer is what we really want to get to is we want to get to where we've got all of the pieces of the puzzle. And right now we've got a small, although it's a very large data set, we've got a small piece of the puzzle. We've got echocardiography and hospitalization records, for example, for NEDA. And with the congenital heart disease program, we've got the clinical information, the diagnosis, the intervention, and their hospital and mortality records. So that's one small piece of the true healthcare intersection. So what we need now is we need to add things like pathology. We need to add all of the other imaging like MRI, CT angiograms, the CT scan. We need to add all of these different aspects to the mix so that we can have this multidimensional space. That my ideal would be that we can invert the way that we practice. In other words, we can have a scan earlier on in life that can either give you a benchmark to work from or an indicator of something that's going to happen over the next few years. You can modify your lifestyle for lifestyle modifiable diseases. You can intervene earlier for things that aren't lifestyle modifiable. But you can invert that relationship so we're not waiting for symptoms to emerge before we're finding patients presenting to their healthcare professional. I think that would be ideal. And if we could get to a point where people volunteered that information on a national scale, we've got the ability computationally now to hold that information and use these modern technologies to understand those clusters and hopefully intervene earlier.
Okay, terrific. Thank you everyone for joining us tonight. I hope that you found it a really interesting discussion. If you do have questions that pop up, as you leave or when you get home, please feel free to reach out to the team, and we'll be very happy to connect in with Geoff, Carmine, and Elle, and follow up on those queries for you. If you've liked or learnt something tonight, please share with your friends, family, get the word out there. We really do need to raise awareness of the work that we're undertaking, and that would be appreciated. I encourage you to follow us on social media, whatever your chosen medium, and to share the word out. And we do have our tax appeal out in market at the moment, and we're focusing on the work that Carmine is delivering in terms of 3D bioprinting and Bringing Hearts project. So if you are able to, any contribution to that tax appeal would be greatly appreciated. I think we've got some wine to give to our panelists as a thank you. We are so grateful for the support. Our friends that's from here at the state, they provide the lovely wines that we serve free of charge and support us greatly. So I hope you enjoy them. Thank you everyone for coming. Our next event will be on the 2nd of July and we'll focus on cardiovascular aging. So we'd love you to join us for that event. So please do pop it into your diaries. But thanks again and enjoy the rest of your evening. Thank you.
Stand up.